To all. Now today, so in the last class, we discussed about Maxwell equations, differential and integral form and their interpretations. Okay, and boundary conditions. In that boundary condition, there are three types of boundary conditions. That is, one is from dielectric and dielectric, and the second one is dielectric and conductor, and third one is conductor and free space. So in the dielectric and dielectric boundary conditions, both the electric field intensity and electric flux density both are same. That already we proved it. Okay. Now today in this class can discuss about conductor and dielectric medium for the boundary conditions. Okay. So in this class, conductor and dielectric. The one medium is conductor and another medium is dielectric. Boundary conditions. Boundary conditions. Okay. Conductor, dielectric, boundary conditions. Now, first we have to draw the boundary. So this is the boundary. This is the dielectric. E of n, natural field intensity and tangential field component, and this is the conductor. This is the conductor. So A, B, C, D. Okay, this is B. This width is del of omega and height is del of h. Okay. Now here in the conductor and dielectric boundary conditions, we have to assume that this conductor assumed to be a perfect conductor. Okay, so conductor must be perfect. There is no lossless. For the perfect conductor, the sigma value is equals to infinity. Sigma value is infinity, and conductivity rho c is equals to 0. Okay, sigma is equal to infinity and rho c is equals to 0. Okay, for this, the material used for perfect conductor is copper and silver. Copper and silver are used for this perfect conductor with the sigma is equals to infinity and rho c is equals to 0 values. Now, to determine the boundary conditions for a conductor dielectric conditions. Okay, now whatever the procedure we are using for find out the boundary conditions of dielectric and dielectric, the same procedure we can using for conductor dielectric boundary conditions also. Okay, so first we have to applying the Maxwell equations for find out these conductor dielectric boundary conditions. So the Maxwell equation integral of E into d of L is equals to 0 for a closed path of A, B, C, D, A. For a closed path of A, B, C, D, A. Okay, A, B, C, D, A. Now, So by applying these Maxwell equations, integral of E into d of L is equals to 0 for these above figures. Now first E of t into, sorry, first A B. From A to B there is no electric fields. Okay, so 0 into del of omega plus BC. BC means again we are conducting, this medium is the conductor medium and this medium is the dielectric medium. Okay, so BC height is del of H. Okay, so there is no field component. So 0 into del of H by 2 plus and a half. Remaining half is, what is this electric field component for the horizontal arm? E of n. E of n into del of H by 2 minus opposite directions minus E of t, because this one, okay, this one CD, here it is forwarding in this direction but current is in this direction, so opposite directions. E of t into del of omega minus E of n into del of H by 2, that is from D to A. Okay, D to A. Okay, minus 0 into del of H by 2 is equals to 0. Total field components E into D of L is equals to 0. Okay, integral of E into D of L is nothing but total electric field for this closed path from A, B, C, D, A. Okay, so this is 0, this is 0 component and this one is 0 component. Okay, now in this equation del of H tends to 0, so del of H tends to 0, therefore this equation, this term is equals to 0 and this term is equals to 0 and the remaining terms is E of t into del of omega is equals to 0, therefore E of t is equals to 0. Okay, now from this, that is tangential component of the electric field intensity is equals to 0. So electric field intensity for the tangential component is equals to 0. Similarly, you can find out the field density, okay, for the boundary conditions. Electric field density D is equals to epsilon into E. Therefore, D of T is equals to epsilon into E of T. Okay. So therefore, but so dt by epsilon t is equals to E of t, but E of t is equals to 0. Therefore, d of t by epsilon is equals to 0. So therefore, d of t is equals to 0. Tangential component of the electric field density, okay, is equals to 0. Then the natural component d of n is also equals to 0. Okay, this is the boundary conditions for the conductor and dielectric mediums. Okay, therefore these two equations dt is equals to 0 and d of n is equals to 0. Okay, and E of t is equals to 0 gives the conditions to be satisfied as the boundary for conductor dielectric medium in which the conductor was assumed to be a perfect conductor. Okay, next. Next, conductor and free space free space boundary conditions. Boundary conditions. So conductor free space boundary conditions. Here, so one is the conductor medium and another one is free space medium. Okay, so what is the boundary conditions satisfying when the field is between the conductor and free space medium? Okay, so first we have to draw the boundary conditions. Boundary conditions and the field components is E. This is E of n. This is E of t. Okay, and this is the free space medium. Free space epsilon is equals to epsilon naught into epsilon r, and conductor E is equals to 0. That already we proved in the last derivations. Okay, the conductor free space boundary conditions is the special case for conductor dielectric conditions. The boundary conditions at the interface between the conductor and free space. The boundary conditions at the interface between conductor and interfacing. Okay. Now the boundary conditions are given directly by substituting E is equals to 0. Okay. So the last derivation of conductor and dielectric is similar to the conductor and free space boundary conditions simply by substituting E is equals to 0 in the conductor and the permittivity epsilon is equals to epsilon naught into epsilon r. Yeah. Now here for the free space medium epsilon r is equals to 1. Okay, relative permittivity is equals to 1. Therefore epsilon is equals to, only you can consider epsilon naught, that is permittivity value. Therefore E of t is equals to 0, that already we proved in the last derivation, and the dielectric electric field density d is equals to epsilon into E. Okay? So dt is equals to epsilon naught into E of t. So E of t is equals to 0. Therefore dt by epsilon naught is equals to 0. Okay? Epsilon naught is equals to 0. And the same thing, E of n is equals to 0. Then d of n is equals to epsilon naught into E of n. Okay, then E of n is equals to 0. Therefore d of n is equals to 0. Okay, so this is the condition to be satisfied when the medium is from conductor to free space boundary conditions. Okay. Next, the Poisson and Laplacian equations. The Poisson and Laplacian equations are easily derived from the Gauss law. Okay, Gauss law is nothing but Poisson and Laplace equations. This equation we can deriving from the Gauss law. Gauss law is nothing but del dot D is equals to, generally D is equals to epsilon into E. Okay, so del dot D is equals to del dot epsilon into E value. Okay, this is equals to rho V. This already we know the Gauss laws. Okay, now E is equals to electric field intensity in terms of potential. E is equals to minus of del into V. Therefore, therefore, now you can substituting this E value in these equations. So what will happen? Del dot epsilon into del V. So it will comes minus. Here it is minus. Okay, is equals to rho V. Okay. Now simply, so del dot del V, that is equals to del dot del dot epsilon into V, epsilon into V is equals to rho V. Okay, negative. Okay, so del dot del, that is del square. So del square V is equals to del square V is equals to minus of rho V divided by epsilon. This is the equation for Poisson equations. Now, for the special case, if rho V is equals to 0, that is volume charge density rho V is equals to 0, that is in the charge of free region, okay, is equals to 0, then automatically this equation, Poisson equation, will becomes del square V is equals to 0. So this equation we can call it as Laplace equation. Okay, this is Poisson equation. Poisson equation. This is Laplace equation. Okay, so this is the boundary conditions and Laplacian equations. Next, so boundary conditions. Next, I will go for plane waves and properties. In that one, we will see the wave equation, Poynting vector, reflection, refraction, polarization, phase velocity, group velocity, like this. Okay. Next, now plane electromagnetic waves. Next one is plane electromagnetic waves. Okay. Now we have to assume that the electromagnetic waves, that is the EM waves. Okay, these EM waves can travel in the x direction, that is the direction of propagation. Okay, direction of propagation. Propagation is nothing but the wave travels in a particular direction. How the waves can be propagated in the free space medium. Okay, in this way, the electric field E is in y direction and magnetic field is in the z directions. Suppose this is z direction, this is x. I'll redraw this one. So this is x direction, this is y direction, this is z direction. Okay. Now here the wave is traveling along the x directions. Okay, the wave is traveling in x direction, then the electric field E is in y directions. So in this direction the electric field is in y direction and magnetic field B is in z directions. Okay, z directions. Now the wave such this, the electric and magnetic fields are restricted to being parallel to the pair of perpendicular axes and are said to be linearly polarized waves. Linearly polarized. Polarization is nothing but it has different types of, that is linear polarization, horizontal polarization, vertical polarization, circularly polarizations, elliptical polarizations, like this. How the waves can be propagated in different ways, whether it is a vertical or whether it is a horizontal or whether it is a circularly polarized, like this. Okay, based on the polarizations can defining the different wave polarizations. Okay, now we have to assume that the point of P and the magnitude is the point of P and the magnitude of E and B or the fields depends upon x and t values. Now, at any point of P, at a distant point, then then the magnitudes of E value electric field and magnetic field magnitudes, okay, depends on x and t only and not upon y and z coordinates. Okay, this magnitudes, the electric field is in y direction, magnetic field is in z directions, but the wave is propagating in the x directions. Okay, so this E and B value depends upon these magnitudes of x directions where the wave is propagating. Okay, this sine wave magnitude and t value. So a collection of such waves from the individual sources is called is called electromagnetic waves. Okay, so the collection of such waves from the individual sources is called the electromagnetic waves. The surface connecting points of equal phase in all the waves called as wavefront. Okay, so different sources, you can collecting all the waves from the different sources with the same phase shift, then that is called as a wavefront. Wavefront. Okay. say geometric planes. In comparison to point source of radiation, sends waves in all directions. If the wave is propagating in all the directions, that is like a isotropic, but none of the antenna can radiate in all the directions equally. So, but all the practical antennas can be as a directional antennas. No antenna is a isotropic. All the directional antennas are propagating the waves in a particular directions. Okay. The surface connecting points of equal phase is a sphere of these situations. Now, the surface connecting points of equal phase is a spherical coordinate. Generally, the coordinates are three types: Cartesian coordinate, cylindrical coordinate, and spherical coordinates. Okay. In Cartesian coordinate, the variables are x, y, z directions, whereas in the cylindrical coordinate, x, z, z, x, y, and pi directions, whereas in the spherical coordinate, r, theta, and phi values. R, theta, and phi values. Okay, r is the radius from the sphere. R is into the point, a distant point, and theta at an angle, and phi is the azimuthal angle. Okay. Now the differential equation relating to B and E, then so the differential equations relating to B and E, okay, electric field intensity and magnetic flux density. When the wave is propagating in the x direction, the electric field is in the y direction and magnetic field is in the z direction. Now, how these E and B are related to x and t and okay. So this electric field and magnetic field are related to x and t values. Okay. Now the relation is dou E by dou x is equals to minus dou B by dou t. Minus dou B by dou t. Okay. And dou B by dou x is equals to minus mu naught epsilon naught into dou E by dou t. This is the relation between electric field E and magnetic flux density B with respect to x and t values. Okay, dou E by dou x is equal to minus dou B by dou t, and dou B by dou x is equals to minus mu naught epsilon naught dou E by dou t, where mu naught is equals to, that is the generally permeability mu is equals to mu naught into mu of r, where mu naught is nothing but absolute permeability and mu of r is equal to relative permeability. Here we can consider as a free space. So in the free space, that is mu of r is equals to 1. So mu is equals to mu naught. Similarly, permittivity. Permittivity. Epsilon is equals to epsilon naught into epsilon r. This epsilon r relative permittivity is equals to 1. Therefore, epsilon is equal to epsilon naught. Now, this from this equation, that mu naught and epsilon naught. So mu naught is equals to 4 pi into 10 to the power of minus 7, and epsilon naught is equals to 36 pi into 10 to the power of minus 90. Okay. So that is equals to C. So this while substituting the constant values of mu naught and epsilon naught, C is equals to 1 by mu naught into epsilon naught under square root. Okay, this value is 3 into 10 power 8 meters per seconds. Okay, this is nothing but velocity of light. Velocity of or velocity of wave or wave speed. Okay, 3 into 10 power 8 meters per seconds. C value. Okay, now this is the free space medium. Now, if the plane waves is in vacuum, assume that now plane waves in vacuum. Plane waves in vacuum. That is nothing but E of then the relation E of z comma t is equals to Ey of z comma t is equals to Ey of z into e power j omega j omega t j omega t, where this is nothing but a phasor. Okay, e of y is equals to e of y of z into e power j omega t, where e of y is nothing but the a phasor. Okay. Now, while simplifying this in vacuum, the phase velocity of the wave equals to velocity of light. Okay, the phase velocity of the wave is equals to the velocity of light c. Therefore, in one-dimensional equations, this equation we can simplify that dou square d square e of yz divided by dz square plus omega by c whole square into e of y of z is equals to 0. Okay. Now, from this equation, how many number of waves the wave number can be find out by the wave number k is equals to omega by c. Okay, where omega is equals to 2 pi f by c, that is equals to 2 pi by f by c is equals to lambda. Okay, generally c is equals to f into lambda, where lambda is equals to okay, lambda is equals to c by f. Okay, so okay, so k is equals to 2 pi by lambda. Okay, this k value you can call it as a wave numbers. Okay, or the one dimension. Therefore, the one-dimensional wave equation, is d square ey of z divided by dz square plus k square, and omega by c is equals to k square ey of Z is equals to 0. Okay. Now this is the second order differential equations. Okay. This equation we can simplify that. So the solution of this equation Ey of Z is equals to Ey of Z is equals to, we can write this equation in differential form a into e power minus j into k into z plus b into e power plus jk into z. This is the solution of second order one dimensional differential equations. Okay. Now Now, if the wave is propagating in the vacuum, then the phase velocity of these traveling waves v of pi is equals to, from this equation, okay, v of pi. When the wave is propagating in vacuum, then the phase velocity of these traveling waves v of pi is equals to plus or minus omega by k, that is equals to plus or minus c. Okay. So the phase velocity for the wave is propagating in a vacuum is equals to velocity of light, that is 3 into 10 power 8 meters per seconds. Next, now when the wave is propagating in the dielectric medium, and the wave is propagating in the dielectric medium. So already we know the different types of boundary conditions, that is dielectric and conductor and free space. Okay. Now, if the wave is propagating in dielectric medium, then the plane waves in a lossless homogeneous dielectric, then the wave number of the wave propagating in a vacuum is a function of permittivity and permeability of the free space. Okay, the plane waves in lossless first point, waves propagating in dielectric medium. In this one, first plane wave in a lossless homogeneous dielectric. Homogeneous dielectric. This one, the wave number for the wave propagating in a vacuum is a function of permittivity and permeability of the free space. That is nothing but k naught is equals to wave number, where k naught is equals to, it is a wave number when the wave is propagating in a lossless homogeneous medium. Okay, so k is equals to 2 pi f into under square root of epsilon naught into mu naught. Okay, generally, in general, the k is equals to, k is equals to 2 pi f under square root of epsilon naught into epsilon r mu naught into mu of r. Okay. So this k is equal to omega by c. Okay. K is equals to omega by c. Now we will see how it will comes. 2 pi f is nothing but omega and the square root of epsilon naught into epsilon r and mu naught into mu of r. Okay, if it is a lossless medium or free space medium, then epsilon r is equals to 1 and mu of r is equals to 1. Then it will comes epsilon naught into mu of mu naught. Okay, then omega, but c is equals to, already we know, 1 by square root of epsilon naught into mu r naught, that is equals to c. Okay, this is nothing but the k value. Okay. Same thing for the lossless medium, k naught is equals to 2 pi f into epsilon naught into mu naught. Next, if the plane wave is generated by a signal generator propagating through dielectrics, two different dielectrics, then then k1 is equals to 2 pi f and the square root of epsilon 1 into mu naught, and k2 is equals to 2 pi f and the square root of epsilon 2 into mu naught. Okay, two different mediums, because permeability is same, but the permittivity of the medium is changes, that is epsilon 1 and epsilon 2. Here it can say that the magnetic constant is same but different permittivities. Then the wave number will be of these two mediums. Okay. Now the signal is traveling with the same distance but will have the different phase velocities. That is nothing but, here depends upon the wave number of two different mediums, then the phase velocity is also different, that is the distance is different. Okay, now the corresponding phase velocity v1 is equals to omega by k1, whereas v2 is equals to omega by k2, omega by k2. This is the equation of phase velocities when the plane wave is lossless, homogeneous, dielectric. Okay. Whereas next the second one is plane wave in second one is plane wave in a lossy homogeneous dielectric. That is nothing but a dielectric material can be lossy, that is exhibit a non-zero conductivity. Rho is not equal to 0. That is nothing but rho is not equal to 0. The non-zero conductivity. In this situation, the conduction current must be added to the displacement current when considering the Ampere's circuit law. Okay, that is nothing but del cross E of r is equals to minus j omega mu h of r. Okay, or in terms of magnetic, del cross h of r is equals to j of r plus j omega epsilon e of r. E of r. Okay. Or this equation I can write it as, that is the displaced current conductivity, current density plus some displacement current. This can be written as sigma plus j omega epsilon into E of r. Okay, r is the distance from the origin when the current is passing from the when the conductor is placed at the spherical coordinates. Okay, now based on these equations, directly we can find out the propagation constant. Propagation constant, some gamma is equals to alpha plus j beta. Alpha plus j beta, where alpha is equals to sigma into under square root of omega by 2 epsilon 1 plus 1 plus sigma by omega epsilon whole square. Okay? Whereas beta is equals to under square root of, so this is mu by not omega. So under square root of mu into epsilon by 2 into 1 plus under square root of 1 plus sigma by whole square. Okay? Sigma whole square. Therefore, so beta is equal to mu into epsilon divided by 2 under square root 1 plus under square root of 1 plus sigma by omega into epsilon whole square. Okay, this is the where sigma is equals to square root of mu divided by 2 epsilon into 1 plus sigma by omega epsilon whole squares. Okay. Now here alpha and beta. This alpha is nothing but attenuation constant and beta is phase constant. So the propagation constant you can defining in terms of attenuation and phase constant. Okay, the attenuation constant, the unit is nepers per meters, and propagation constant, sorry, phase constant beta is in radians per meters. So that is the unit of attenuation constant and phase constant. Next, next one is it. Two approximations we are using for frequently used is a dielectric with a small losses. A dielectric with a small losses, that is nothing but sigma is very less than a dielectric with small losses, sigma is very less than omega into epsilon with high frequency approximation, with a high frequency approximation 1 plus under square root of 1 plus sigma divided by epsilon omega whole square is approximately equal to 2 is approximately equal to when sigma is very less than omega into e. Okay. Now the approximate value for the attenuation and propagation constant for a small loss alpha is equals to sigma by 2 into under square root of mu by epsilon, and beta is equals to omega into under square root of mu into epsilon, and corresponding phase velocity v of phi is equals to 1 divided by is approximately equal to 1 divided by square root of mu into epsilon. Okay, this is the attenuation constant and phase velocity. Phase velocity when a dielectric is a small losses, that is sigma is very less than omega into epsilon. Okay, so in this situation the phase velocity and group velocity are same. This is also equals to v of g. Okay, group velocity and phase velocity are also same. Also some of the attenuations are introduced. Next, and the second thing is, next one is a dielectric with large loss sigma is very greater than omega epsilon with low frequency approximation then in this case this equation 1 plus sigma divided by omega epsilon whole square under square root of is approximately equals to sigma by omega epsilon, because sigma is very greater than omega epsilon. Okay, this one is you can neglecting and this one is also you can neglecting, and the square root cancel, then it will comes sigma by this one. Therefore alpha attenuation constant alpha is equals to under square root of omega mu sigma by 2, that is also equals to beta. Okay, attenuation constant is equals to phase constant, that is equals to omega mu sigma divided by 2. Okay, if it is dielectric with large loss. Okay, now from these two equations can defining one more term, can introduce the new term skin depth. Some delta is equals to 1 by alpha, that is equals to square root of 2 divided by omega mu and sigma. This is square root of, okay, or 2 divided by omega is equals to 2 pi f mu and sigma. 2 to cancel under square root of, that is equals to 1 divided by square root of pi f mu sigma. This is for skin depth is in meters. Okay. So the skin depth decreases with increase in frequency. Okay, because of the skin depth is inversely proportional to the frequency. If the frequency is increases, then the skin depth is decreases. Okay, next. Next we're defining reflection and refraction. Reflection and refraction. Reflection and refraction. Now, suppose this is the medium, this is for air, this is for water. Okay. Now, when the wave is incident to the medium, this is the medium. Okay. Now, if see, this is incident wave, this is reflected wave, this is refracted wave, this is the origin. If and this is nothing but wait, I'll redraw this one. So this is nothing but angle of incidence this is angle of reflection, this is angle of refraction. Now, so first, what is the definition of reflection? Okay, So the reflection is nothing but is the abrupt change of the direction of propagation of a wave that strikes the boundary between the two different mediums. So reflection is the abrupt change in the direction of propagation of the waves. Okay, abrupt change. Now here the wave is incident to the boundary from the air medium. When the medium is changes from air medium to water medium, the wave is abruptly changes to some angle. Okay, that is the reflection. So the strikes the boundary between the two different mediums. So where it can changes means when the wave is bombarded on the boundaries between the two mediums. Okay, so at least a part of the incoming waves disturbances remains in the same medium. Regular reflection, which follows a simple law, occurs plane boundaries. Okay, so the angle between the direction of motion of the incoming waves and perpendicular to the reflected surface, that is the angle of incidence. Okay, whereas refraction is the change in the direction of the wave passing from one medium to the another medium, another medium. Now see, this is the incident waves. Okay, it will crossing the boundary, but it will change the direction. Here, it is not to the straight. Okay, when passing from one medium to another medium, whereas reflection in the same medium, it will change the direction when it is bombarded on the boundaries. But in the refraction, the wave is crossing the boundary from one medium to the another mediums. Okay, when the suppose when the wave is traveling from air medium to water mediums, for example, so the wave in deep water travels faster than in shallow. So if it is in the ocean wave approach, the beach obliquely, the part of the wave further from the beach. Okay. Next, the phase velocity is nothing but the wave is the rate at which the phase of the wave propagating in the space. Okay, the phase velocity is nothing but the wave is the rate at which the plane of the wave propagates in space. Whereas in group velocity is the velocity at which the variations of the shape of the wave amplitude, that is the modulation or envelope through the space, is nothing but group velocity. Okay, so finally we can conclude that. So I can conclude that of the today's session, boundary conditions of dielectric, conductor and conductor free space medium, then plane waves with the different mediums, that is the lossy and lossless, phase velocity, group velocities, and a reflection and a refractions of the waves traveling in the free space medium and dielectric medium with the lossy and lossless. Okay, so thank you.